So we left off about halfway through section 6.1, and what we're going to do now is kind of pick up with an example of how to use the Laplace transforms in order to solve a differential equation. So we're going to start with a relatively simpler one. This probably brings back memories of chapter 1 when we were just dealing with a single differential equation that was linear and was, in this case, a first order differential equation. So pretty straightforward. We have our initial condition and we have our differential equation. So together that gives us our initial value problem. And so we could, if we wanted to, go back to section 1.8 or 1.9 to be able to use a technique like integrating factor or the lucky guess method, as we call it. But really it's about, in this section, about coming up with another solution method. So what we're going to try to do is we're going to use the Laplace method. And so we're going to call this the Laplace transform method. And in order to use this method, we need to apply the Laplace transform, just like we would apply the derivative or apply natural log or apply any operator to our differential equation. So we're going to apply the Laplace transform to the entire equation here. And so when we do that, I'm going to use multiple colors here to kind of keep things straight. We're going to apply the Laplace transform to our entire equation. Oops. Keep the color scheming the same here. And when we do that, applying the Laplace transform to the entire equation, because the Laplace transform works like the limit operator or the derivative operator, it takes each term as a separate thing. So we can say, okay, so let's apply the Laplace transform to our derivative, dy dt. The other side of the equation is the Laplace transform of y minus the Laplace transform of 4e to the minus t. And so right out of the gate, we have a situation where if we know how to take the Laplace transform of dy dt, then we can proceed. If we know how to take the Laplace transform of just y, or y of t, well, we know that is just going to be our capital y of s. That thing right there is what we're playing around with. And over here, we've got the Laplace transform of some exponential function. So we know how to do each one of these thanks to the table from the previous page. So if you remember from the previous page, or previous pages, we know that this thing right here can be written as the Laplace transform, s times the Laplace transform of y minus the initial condition y of 0. Right. And so that's the left-hand side of the equation. The right-hand side of the equation, well, it's just the Laplace transform of y, whatever that happens to be. Minus, then the Laplace transform of this, if we use the table, and actually we're using the table for both of these, we find out, you flip over to the previous page and you find out that you can pull that -4 out front, and it's -4 times the Laplace transform of e to the negative t, which is 1 over s plus 1. Right? And this is true, just as a side note, this is true as long as s is greater than -1. Right? So we kind of keep that in our pocket on the side, that this is true as long as s is greater than -1. So over here, it turns out that we have an initial condition given to us in the problem, way up here at the start. We know that y of 0 equals 1, so that's what we're going to replace right there with just a 1. And so continuing on, I'm going to scoot this up a little bit. We have s times the Laplace transform of y minus 1. The other side is the Laplace transform of y. And then over here, this is, well, just tidying things up a little bit. Now, what we have is an equation that involves the variable s, over here and over here, plus this other thing, the Laplace transform of y. And that's really what we're trying to solve for. So I'm going to move my Laplace transforms of y all to the same side and move everything else to the other side. So with a little bit of algebraic manipulation, if I subtract the Laplace transform of y, I'll have s times, oh, excuse me, not s times, s minus 1. Trying to get fancy and do too much in one step here. S minus 1 times the Laplace transform of y, after we factor that other side. And this, if I add the 1 to the other side, I'll have 1 minus 4 over s plus 1. Now, I'm not done yet because I'm trying to solve for this Laplace transform of y. This Laplace transform of y is then therefore going to be equal to, if I divide both sides by s minus 1, I'll have 1 over s minus 1 minus 4 over s plus 1 times s minus 1. So what we have here on the left-hand side is we've just solved for the Laplace transform of y. The solution to this differential equation is y of t. I know the Laplace transform of that solution. And I know it's got to be equal to all this stuff on the right-hand side. The problem is that I don't really know what the solution is, but I do know what its Laplace transform must be. So I'm going to write that underneath here. I'm going to say that all this stuff over here, this must be the Laplace transform, I'm going to abbreviate here, the Laplace transform of the differential equation's solution, y of t, right? So I know this thing is the Laplace transform of the solution. The only problem is I don't know what the solution is. So notice at the bottom of the page it says this yields the Laplace transform of the solution of the initial value problem. So that means we solved the initial value problem and didn't need any calculus to do it. We just needed a table with some Laplace transforms. The problem is that we didn't actually solve it. What I need to be able to do now is undo. Because if I can undo this Laplace transform on this side with, say, an inverse Laplace transform, I can undo it and it becomes y of t. But that means I also have to be able to undo the Laplace transform on the other side. And so that's what we're going to do on the next page. So at the top of the next page, so for the previous example, we can say that with a little bit of manipulation. If I scoot these two guys together, I get this bigger fraction. The problem is that that equals this doesn't really help me solve y of t. So I kind of helped kind of squeeze things together. But if you look at the table, we don't have an exact match in our inverse Laplace table for this form. So that means, unfortunately, we can't just use the table to jump right to a solution. But we can do some practice with the table in order to figure out how to undo the Laplace transform. So down on this page, you'll see there's some examples of how do we undo the Laplace transform. And the first couple are pretty straightforward. If you take a look at the table from several pages ago now, so I can turn my notes back and see if I can find that table. Eventually I'll find it here. Oh, by the way, this is the table where we saw the Laplace transform of the derivative. Looks like this. The Laplace transform, the sum and difference rules, as well as the constant multiple rules are there. But the previous page before that, in the notes, we had the table where we know if we go this direction, we're taking the Laplace transform. If we go this direction, we're taking the inverse. And so if you take a look at our examples here, 2 over s cubed, no. That's probably going to be the form that we're going to use. And so 2 over s cubed, the bottom, s is s to the power of n plus 1. So if it's cubed, then that means n is 2. 2 factorial is 2. So that's the form that we're going to use. That means if I inverse the Laplace transform, it's equal to t to the second power. So this, really, right here, is the same thing as saying t squared. So by applying the inverse Laplace transform, the t, in this case, it's equal to t squared. And that's because we use the rule where it's n factorial over s to the n plus 1, right? That was the rule that we used. I gotta tell my dogs to be quiet. Okay, now that the dog has settled down, let's take a look at the second example. This one's got a constant up top and then an s squared plus 9 down in the bottom. And if you're noticing the 9 and thinking, well, that's the same thing as s squared plus 3 squared, you're on to something. And so if you look at your table, take a second and take a look at the table and see if you can spot which one of these looks the most like what's going on. So if you notice, these two look an awful lot alike. But do you spot the difference? Hopefully you do. The top of this one is the constant omega. The top of this one is the variable s. So in this case, we have a constant up top, which happens to be the same constant that gets squared right here. So that for us, we're going to be following the rule that says omega is equal to 3 in this case. And if we apply the rule, we can see that that's really just the sine rule. So it's sine of omega, or 3, times t. So those first two, it was really just reading the table to make sense of what's going on. But this last one, it's a little bit different. So if you're taking a look at what's going on, you might say, okay, there's the example that we're trying to solve. And so if you go down the list of all the things in our table, which one does it look the most like? We've got s minus 1 up top, and then in the denominator, we've got a quadratic. And so you notice, and it can't be this one, can't be that one, can't be this one. It could be that one, but it's not. This isn't a quadratic. This would be a 4th power down here. So it's not that one. Can't be that one. Can't be that one. Nah, because it's more than what's going on in the basement there. Oh, now we're on to something. This one has some promise. This one, of course, it's not s squared in the numerator. This one has some promise. The problem is that if a in the top equals 1, then I'm going to have to rewrite the denominator so that it's a perfect square plus something left over. And so that's what I'm going to try to do here. A perfect square in the denominator. So if you notice, this could be rewritten as the inverse Laplace of, up top, s minus 1. And in the bottom, I'm going to take these first two terms and try to play around with them. And if I can make a perfect square out of that, then we're in good shape. So off to the side, you might say, okay, if these two terms become my perfect square, then what do I have to add and then, of course, subtract at the same time in order to make this work? Well, s squared minus 2s plus 1 would give me a perfect square. But then I'd have to subtract 1 as well. So these two terms right there, I have to do my little completing the square trick. And so the first one, s squared minus 2s plus 1, gives me the perfect square of s minus 1 quantity squared. But then I have the minus 1 left over with the plus 5. And so that resolves itself pretty nicely. And so we're really taking the Laplace transform of s minus 1 over s minus 1 quantity squared plus 4. A little bit of algebra. The kind of algebra you either absolutely adored or hated in pre-calc. And you find out that as long as you're playing this game, and you can say here that a equals 1 for us, and then over here, this is our omega squared, so omega is equal to 2 in that situation. That means that I can rewrite my Laplace transform as the solution e to the t, e to the 1t, times cosine of 2t. So in all three of these examples, we can use the table, even though we might have to manipulate it a little bit to kind of figure out what's going on. So we have, hold on a second. So what we're going to do now is I'm going to end this video, and we're going to start the next video by taking a look at one more, a little bit more complicated example of an inverse Laplace before we finally circle back around and solve our the problem that we've been working on since the beginning. So we're going to stop here, and you can check it out on the next video.